we have selected these questions from last year midterm and final exams. And in this slide, you can see the questions that we will try to cover today. I don't know if we will have time to cover all of them, but we will start from the beginning. As you can see, the first one is about GPUs. The next one in DRAM bitmap is related to Ambit. Then we have cache questions. We have more SIMD, DRAM refresh, more caching and PIM, etc. So we are going to start with the GPU and SIMD question, and Jeremie is going to solve it. How many people here are going to take the exam? I guess 1, 2, 3, 4, 5, 6 people. Okay. That's good. Just let me give you a reminder. Tomorrow we will try to start the exam at 12 because the exam is supposed to last for 180 minutes. So we will try to start at 12 or 12:02 or something like that for you to keep that in mind. Okay? When you're ready.
Okay, so this is the GPU and SIMD question, and here we're trying to find the utilization of these GPU warps. And so the question says, we define the SIMD utilization of a program run on a GPU as a fraction of SIMD lanes that are kept busy with active threads during the run of a program. As we saw in lecture and practice exercises, the SIMD utilization of a program is computed across the complete run of the program. The following code segment is run on a GPU here, and each thread executes a single iteration of the shown loop. So assume that the data values of the arrays A, B, and C are already in the vector registers, so there are no loads and stores from this program. And note that there are 6 instructions per thread. And so here we can just label the instruction numbers. There's 1, 2, 3, 4, 5, and 6. And so basically, we're unrolling this loop across all our given threads, across all our warps on this 32 SIMD lane GPU. And so given that we have 1,008 loops here, and our GPU warp size is 32 threads, we have to have the seal of 1,008 divided by 32, and that turns out to be 32. So that 32 is the number of warps that you need. And note that we have 31 fully utilized warps, so 31 by 32, and then one of them are half utilized because we have 16 remaining loop iterations that we need to compute with this last warp. So the next question asks what the maximum possible SIMD utilization of this program is. So basically, we want to compute how many of these threads per warp are actually doing something important across this entire program. And so we can we assume that for the maximum utilization case, we have no branch divergence, which means that every instruction is running the same instruction, right? And so if you do have branch divergence, some of your threads in your warp might not be executing because now you're on an instruction that doesn't necessarily need to be run by that particular instruction in the warp. And that happens when at least one of your threads per warp needs to execute an instruction. And this is just to guarantee that every thread per warp is on the same instruction. And so the maximum possible utilization here is, let's just pick a case where they all execute instruction 1 here, and then they also all execute instruction 2 here. And these are necessary because they're part of the loop. And number two, you have to evaluate your comparison to see whether all of the following instructions need to be done. And so let's just assume that there's no branch divergence, and this branch is not taken. And so everyone just computes these two instructions. And so the maximum possible utilization here is just a ratio of the number of warps you have versus the number of threads that you have running versus the total number of threads that are contained in every single warp that you have. And so this just comes out to be the ratio of 1008 over 1024. Yeah, any questions? So the next question asks, to describe what needs to be true about arrays B and C to reach this maximum possible SIMD utilization asked in part B. So it wants you to cover all these cases where we have no branch divergence at all. And so let's just go back to the function here. And so the first case is when this branch is not taken. And so this is true when B times C results in all of these values being greater than or equal to 0, right? And so you can enumerate that yourself. And then there's also the case where this branch is taken by all threads, and then the next branch is all taken by a single warp, by all threads in a single warp, or all not taken in a single warp. And so either C of I has to all be lower than 0, or all be greater than or equal to 0, right? The next question here asks what the minimum possible SIMD utilization of this program is. And so basically, we want to maximize the denominator, which is the number of threads that are being used across all warps, or not being used, but that are part of all warps that are executing all these different instructions out of all of the threads per warp that are actually doing things, or the opposite way around. And so here we have these 6 instructions that could potentially be executed, and we can maximize our denominator by making sure that every of these warps need to execute every single one of these instructions, right? And so out of our 32 warps, we have 32 threads, and we have these 6 instructions. And so our denominator here would be just 32 times these 6 instructions. And this is the number of warps, and this is the number of threads per warp. And so looking at the numerator now, we basically have to ensure that every, or at least one thread per warp is forcing all of the threads in a given warp to execute every single instruction. And so again, these first 2 instructions, they have to be executed by all of these threads. And then we can have the case where only one thread per warp is executing these next 4 instructions. And so to calculate this, we would simply do 32, which is the number of threads that need to execute this, plus 32, which is the number of threads that need to execute this, and then 1, 2, 3, 4, so plus 4 per warp. Yeah, 4 instructions per warp, and 31 of these are these full warps, and then we have another of this half warp that needs to also do the same thing. And so we're looking at 16 here, and then plus another 16 for the next instruction, and then also another plus 4. I think that's correct. Yes. Are there any questions here? Great. So the next question here is asking what needs to be true about arrays B and C to reach this minimum utilization. And again, we have to cover all these cases. And so in order to actually get the case where one thread per warp is executing these next 4 instructions, we want to make sure that this holds true for 1 and this holds true for 1. So you're forcing all these different threads per warp to go through with this single thread per warp, right? And so if this is true and this is true, then it turns out that there's only really one case where this happens, where one C of I per every 32 groups is less than 0. And then because all these are less than 0, you have to ensure that this is greater than 0. Yeah, this is greater than 0, so that A will evaluate here for that single thread per warp. Any questions? So the next question here talks about dynamic warp formation, which is used to improve the SIMD utilization, and DWF, or dynamic warp formation, dynamically merges these threads executing the same instruction after branch divergence, so that if you can minimize the number of warps that are in flight, and this will help you increase your utilization. So so they're asking for what is the maximum achievable SIMD utilization when you do have DWF. And so here we go back to the function. Basically, when you have all these cases again, where you have one thread per warp executing these 4 instructions, and then all of your other instructions are executing these ones, you note that there are 32 warps, right? And you have 1 thread per warp that's executing. And so given that information, you can basically take all of your threads that are executing per warp on these 4 instructions and merge them into a single warp. And so now you can maximize your utilization with that. And so to calculate this, you would have, let's see, you'd have all of your instructions here. So so you'll have 32 instructions here, plus another 32 threads here, 32 threads here, and then you multiply that by the number of warps that have this many threads executing. And then you also have another warp that's half full again here. So you have 16 plus 16. And then for the rest of these, you have a single warp that's executing all of your threads combined. And so here we have plus 32 times these 4 instructions, right? And so this comes out of all of the threads that we're executing, which would be 32 plus 32, and then 32 because your half warp has to be running as well, and also plus 32 times 4 for the rest of these instructions. Yeah.
Would it really be enough to leave the formula at the end during the exam, or do we have to?
Yeah, you don't have to reduce it, but try to reduce it as much as you can. Yeah.
So, do we have to, do we get full points if we would write that?
Like this?
Yeah, or do we have to add the stuff up and multiply things up?
I think this should be fine. Yeah. As long as you show you know what you're doing, it should be okay.
Or I don't know this one. Okay, so first we are going to solve a question that is about in-DRAM bitmap indices. So basically what it's saying here is for you to remind that we study ambits in class. That is a DRAM mechanism that can do bitwise operations inside the DRAM chip. And here I'm saying that you have a database, that in the database you are storing you are basically storing, you have some users and you have the weeks. And you want to know if that user was active in the database in that past week. So if the user 0 was active in the system in the week 0, you put a 1 here. If user 1, then you put a 0 if was not activated. So you have basically U users and W weeks in total in the database. And each position holds 1 or 0, 1 bit. I don't know if I was showing properly. So here are saying that you should assume that the bits corresponding to 1 week are all in the same row. And also it's important to know that the total number of bits in a row is 8 kilobytes in the DRAM row. And if you can have as many rows as you can have more rows in different subarrays that are also possible to execute the ambits operations. So the user wants to find out the query, how many unique users are active every week for the past W weeks. And then you have two implementations to solve this problem. The first one is a CPU-based implementation. The basically is going to read the whole database and do end operations between the weeks, and then count the number of the results that was 1. And to do so, to simplify the question, you assume that the bottleneck of the CPU is the memory, and the execution time can be defined by that. And you have a memory that can provide X bytes per second. And also we have our ambits implementation, and you have to assume that you can take advantage of the end operation in this case. Each subarray has 1 row for accumulation and 1 row for the operand. So basically what you have to do is to copy the data to the operand and then do the end with the accumulation. And then if you want to do the computation with the bitmap, this bitmap computation to know how many users is going to be done on the CPU. So in the ambit implementation, you have 2 parts. The first part is to do the end operation, and you have the second part is to compute the bitmap. And this is done by the CPU. So the first question here asks, what is the total number of DRAM rows that are occupied by U users and W week? So remember that you have this structure, user 0, user 1, user 2, so on and so forth. So you have U users here, and here we have week 0, week 1, so this is W. So basically, you're going to, and these users are stored in DRAM rows. So basically, what you're going to need is you have the users, and you know the size of the, the size of the DRAM row is 8 kilobytes, but the users are bits, so you have to multiply by 8. And then you have W weeks. So this is the total number of DRAM rows that are going to require for the total database. Any question here? Okay. So then they ask what is the throughput in users per second that ambit-based implementation is going to take. So you first need to know how much time ambit is going to take. And remember that the time is the time to do the ambits operation and the time of doing the bitwise computation, the bit count computation by the CPU. So the ambits operation, basically what you have to do is first copy the, as I said before, to do the ambit, you do the copy of the row, and then you do the end. And in the question they say that the time to do the copy is TRC, because we are using row clone, and the time to do the end is TEnd here. So in total, to do the time of ambit is going to be the total number of operations that you have, U divide by 8 times 8k times 8. This multiplied by the time of doing the copy plus the time of doing the end operation. And you also have the time of to copy the data back to the CPU to do the computation. This second part here. So in the end, you have going to have the U users, and the throughput of your memory is X bytes. So you're going to take X times 8, because it's bytes, to do the computation. So the total answer is going to be U times 8 plus 8 kilobytes. Oh, this is W. Times W multiplied by TRC plus TEnd plus U divided by X plus. Don't need these bits. So any question here? Okay. So then we ask what is the throughput? Oh, this is in users per second. This is the time. You just divide by users. Then you ask the same, but for the CPU. So what the CPU has to do basically, it has to load this whole table here from memory and do the computation there. So the size of this table is U plus W, and it takes X bytes per second, so 8 bits per second to load everything. So in the end, you're going to have this is the seconds. So the throughput is going to be U divided by U times 8 divided by X plus 8. So it's only this. So then you ask what is the maximum W for the CPU implementation to be faster than ambit-based implementation. So basically what you want to have is the time of the CPU to be bigger than the time of ambit. And in the previous question, you know that the time of ambit is U divided by 8 times 8k multiplied by W multiplied by TRC plus TEnd plus the time of the CPU, that is U divided by X8. So you need this to be bigger than the time of to be smaller than the time of CPU, that is U divided by U times W divided by X plus 8. So you basically need to solve this equation. Again, try to reduce as much as possible in the exam, but it's more important to show your reasoning behind the question. So any question for this? Any questions for this? For this one? Okay. So then you have the second question. There is a cache performance analysis question. So basically, in this question, we have two algorithms, and you want to measure some details about your cache system. So the first code loops over the one array data, and this data holds an unsigned integer, and the size is 32 bits, so 4 bytes. And you also compute the latency of each access here. And you're saying, in the question says that for you to think that this array latency is not cached. So the only thing that is in the cache is the data array. So the first code is going to test basically code access. So you are loading the data and checking the latency, and the second one, we are going to warm your cache first, and then you're going to check the latency. The question, they also say that the cache hierarchy has 2 cache levels. So we have L1 cache, so you have your CPU. You have a L1 cache that is 4 kilobytes, and you also have a L2 cache, and then you have the main memory. So in the first question, they say that we are running the code 1. So basically, we are checking for, we are not warming the cache at all. And you obtain the latency values in the plot below. For the first 64 reads of the array data, so the first 64 iterations of this loop here, and the stride is equal to 1. So I'm going through all the elements of the data array, the first 64 elements of the data array. So the first thing they ask, what is the cache block size in L1 and L2 based on this plot? So the first thing you have to understand from this plot, that this bigger latency here, this is the latency of the cache, should be the latency of L2 miss. And this other latency here is the latency for L1 miss. And here is the latency for L1 hit. So here basically I'm missing on my L1 and I'm hitting on my L2. But in the other one I'm going to miss on L2 in this one. So, and here I have the iteration. So I'm going to block element to element. So I'm going to every 4 bytes. So since I'm checking every single element to know the cache block size of L1, I just need to count how much took for me to obtain an L1 after the first access. So here, if you count, I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 cache hits in L1 before missing and going to L2. So the cache block size should be okay. The cache block size should be 8 times the size of each element, that is 32 bits or 4 bytes. So it's 32 bytes. And for L2 is the same. You just count between 2 consecutive L2. And if you count, you're going to see that it's 32. So it's 32 bytes. This is 128, right? The block size. Any question here? Okay. And then they are saying that using code 2 with stride 1 equals to stride 2 equals to 32. So basically I'm going to every single, I'm going to 32 to 32 elements until 156. And then size 2 is 1K. We observe a latency of 0 of 300 cycles. So basically I'm missing on my cache 1 when I try to access elements 0 again. So I load data here, and then I check the latency for the in the second loop. But when I execute I check the first latency for the first element, I get a cache miss. However, if size 1 is 124, the latency 0 is 100 cycles. So I got a cache hit in this case. Based on that, they want to know what is the maximum number of ways of L1. So basically what the algorithm is doing, assuming that this is your data array, We are going until 1056 here. And each element here is, this is element 0, then I access element 32, so on and so forth. So in total, I'm going to have 32 iterations of this loop, because I'm running until 1056. But the thing is, when I access this last element here, this is 124. When I access element 124, I'm evicting the first element because it was a cache miss in this case. So this element in the second loop is not going to be there. However, if I access until the previous one, if I access until, this is 99.2, I guess. If I access just until the previous one, for the other strides, I don't evict these elements at all. So it means that the maximum number of ways is the maximum number of iterations in this case, is 32. So the number of ways, the maximum number of ways is 32. Okay, any question here?
Why is it 32?
Sorry?
Why is it 32?
So if it was 64, for example, when I access this element here, I wouldn't replace it with 0. I would just put on the 33 way. So when I check the next loop, I would get a hit also. Does it make sense? Any other question? Okay. So now basically you want to find out the replacement policy for this question, for this cache. So it's going to be either LLU or FIFO. So assuming that you're going to run first the codes 2, which stride 32 and size 1K, and stride 2 is going to be 64, and I'm going to run until 1056. Then after resetting my J flag, my J counter, we are going to run the first code, so it's the one that does not initialize the memory, the cache, with stride 32 and size 1K. We are going to observe the latency to access the first element is going to be 100 cycles. So I got a cache hit. So this is a cache hit in L1. So how can we find the replacement policy based on that? So first, what we did for the first run, you are basically doing the same as the other question. So you access elements 0, 32, 64. And then you run it, this is the first iteration in the loop. And in the second iteration, I'm going to access 0, and then I access 64, and so on and so forth. So I didn't access element 32 in the second run. So when I run the second code, I got back to accessing at a stride 32, but I got a cache hit for when I tried to access the second element. So this element here was not replaced, even though it was not less recently used. So the policy cannot be LRU in this case. It needs to be FIFO. Any question here?
Why doesn't the size matter? Like the cache is 4 kilobyte L1. So
why the cache matters?
the L1 cache is like 4 kilobytes.
Yes.
So shouldn't it fit all into the cache?
So it's not going to fit because, oh, I forgot to say something. You have to assume the same associativity as the maximum one that you found before, 32.
Oh.
So it's basically that. Any other question? Okay. So finally, you are going to run you are going to run twice the code 1, and for different sizes. So here, in the first run, stride is equal to 1. In the second run, stride is equal to 16. We ignore the latency result of the first run and average the latency result of the second run. So here is average of the number of runs. So, and then you obtain the follow graph. So what can you talk about these arrows based on this graph here? So check that between until arrow 1 here, I got cache hits in L1. So basically here I have cache hits in L1. But after some times I had cache misses in L1 also. So this point exactly here can detect the size of the array, that the size of the number of times that you run is basically the size of your cache. Because after that you're going to start missing on the cache. So here should be less or equal to 4 kilobytes. That is the size of L1. So from 2 to 3, you only have cache hits in L2. So here you're having cache hits in L2. So the same logic applies for point 3. This is your size of your L2. And between 3 and 4, basically you have some of the elements hits in L2, but you also had misses in L2. And after point 4, everything starts to miss in L2. So I'm paying the 700 cycles. So these are misses in L2. So basically this is your latency to access memory. So this is the solution of the last part. Another question? Okay, so that is all. Who's the next one?
Okay, now the question that we are going to solve is about SIMD. This question was part of last year midterm, and it is about vector processors and array processors, as you already know them. Okay, so as you can see, the question starts saying we have two SIMD engines, one is a traditional vector processor and the other one is a traditional array processor, and they can have a vector length of up to 16. All instructions can be fully pipelined, and we are given some latencies for the instructions. As you can see in the table, this is the ISA that we are going to consider in this question. We have vector add, vector move, shift right, load and store from memory, and these are the cycles for every single operation, assuming in case that the vector length would be 1. So all vector instructions operate on vector length, vector load, and vector store here. And then we have 8 vector registers from VR0 to VR7, each contain up to 16 elements because that's the maximum vector length that we can have. We also have scalar registers, and this is actually important. The memory, it's a banked memory. It has 16 banks, and each of them can be accessed independently. We have to understand here that we have a memory port per bank. One memory port means one address generator per bank. Okay? This is something that we have to take into account. So part A says which processor, the array or the vector processor, is more costly in terms of chip area. So you might remember from the lecture where we were talking about array and vector processors that for array processors we need to have as many processing elements as the vector length. In the case of the vector processor we just need one processing element. So in this case the answer is that the array processor is going to be more costly in terms of chip area, essentially because it needs 16 processing elements versus one processing element in the vector processor. Okay? Any question? Okay, then let's go to part B. It says the following code takes 52 cycles to execute on the vector processor. We have these three instructions: vector add, and vector multiply. As you can see, all these instructions are dependent on the previous one. So the vector mult instruction is dependent on the previous vector add, and the vector add is dependent on the previous vector add. So we cannot execute them in parallel. We cannot pipeline them. If we draw some kind of timeline of the execution of these instructions, we will see that for the very first element in the vector add, we need 5 cycles, as it's stated in this table. For the vector mult, we will need 15 cycles, as you can see. So for the first vector add, we will need 5 cycles for the first element, and right after that, because the vector operation is pipeline, right after that, we are going to get the result for one vector element every cycle. So it will be something like this, VLEN -1. It's also important to consider here that something I forgot to mention before is that there is no chaining in this processor. So it's not possible to overlap the execution of this first vector add with the next vector add after finishing for the first element. So we will start with the second vector add after completely finishing for all vector elements with the first vector add. So then we have again 5 plus VLEN -1, and then we have the vector multiply operation. This is 15 cycles plus VLEN -1. And now we know, according to the question, that all this process takes 52 cycles, and this is equal to 25 plus 3 times vector length -1. So from here we can obtain VLEN is equal to 10. Is that clear? Okay. Yeah, so that's for the vector processor. And now the next question says, oh, how long would it take to execute on an array processor? So keep in mind that in the array processor, what we are going to have are like several processing elements that can execute operations in parallel. In this case, the question says that we can assume that we have VLEN processing elements. And now, because, as I said before, these 3 instructions, V add, and vmul, and depending on the previous one, we cannot overlap their execution. We cannot pipeline them. So that's why we will have to completely account for the total latency of each of the 3 instructions. For the vector add instructions, we need 5 cycles. For the vector mul, we need 15 cycles, total 25 cycles. Is that clear? Okay, I guess so. Let's go to the next part, to part C. It says the following code takes 94 cycles to execute on the vector processor. We are again working with the vector processor. This is our code. We have 2 consecutive vector loads. Then we have 1 vector add, 1 shift right, and 1 vector store. Assume that all the elements loaded in VR0 are all placed in different banks. They are all in different banks in this first vload, and that all elements loaded in VR1 are also are placed in the same banks as the elements in VR0. Similarly, the elements of VR2 are stored in different banks in memory. And it says, what's the v-length of the instruction? So let's draw a timeline same as we did before. For the first vector load, we will need 20 cycles for the first vector element, and after that we can get 1 new element every cycle. Now, one interesting thing to observe here is that because we have 1 address generator per bank, we have 1 memory port per bank, it is possible to start loading the first vector element that goes to VR1 as soon as the first vector element of the previous load is already accessed, because the bank is free. Because the bank is free, we can then start the execution of the second vector load. So after vlen -1, we will have all the elements in VR1 loaded. Next thing we have is the addition. Because there is no chaining, we cannot overlap with the previous operation, with the previous load. So this is 5 plus vlen -1, and then we have the shift right. This is 1 cycle plus vlen -1, and finally the store operation takes again 20 cycles plus vlen -1. Yes?
Is it written somewhere as the memory is multi-ported, or why can you overlap the reloads?
Yeah, this is because we are assuming that there is 1 address generator in each bank. So as soon as the first bank, bank 0, is free, has completed this access, we can start the next access.
And it could also be that the VLAN is large enough that the first bank is needed again for the first VLAN.
Say again? The first bank?
If the vector length is long enough that the VLOAD, as the first VLOAD needs the first bank again, can it interleave this?
Yes, yeah, that could happen. But let's see. This could be like making an assumption, right? And let's see if the numbers match. Okay? And they are going to match. So you will see that 94 cycles are equal to all these cycles that we are considering here. This is 66 plus 4 times vlen -1. And this gives us vlen equal 8. Okay? Yeah, now let's go to the last part, part D. It says we replace the memory with a new module whose characteristics are known. The following code takes 163 cycles. This is wrong, actually. This is 170 cycles, is what we have to consider, to execute on the vector processor, and then we have a similar, it's actually the same code here, right? Load, add, shift right, and store. Now we know that what's the vector length. It is 16 this time. The elements loaded in VR0 are placed in consecutive bands. The elements loaded in VR1 are placed in consecutive bands, and also the same for the store operation for VR2. What is the number of banks in the new memory module? So now, what we have to keep in mind is that as opposed to what we had before, where we had for the first vector load, you remember we had 20 cycles for the first element and then VLAN cycles. Now, the problem that we have is that we know that the number of banks that we are going to have is smaller than before. Why do we know that? Because this module is somehow less equipped, right? So in the past, for the same code, we needed 94 cycles. Now we need 170 cycles. So this means, or it's giving us a hint, and the hint is that the number of banks now is smaller than before, right? And if the number of banks is smaller than before, and because VLAN is 16, we know that we cannot serve all the accesses for all the vector elements in parallel. So this means that after the first access for the first element, we will have another access, another 20 cycles to the same bank, to bank 0. And this might happen several times, depending on what's the number of banks that we have. So this would be again 20. And when we finish, we will still have to wait for, when we finish with the first bank, with bank 0, we will still have to wait for as many cycles as the remaining number of banks. So that's why we will have to wait here for bank -1, right? One interesting thing that we have to keep in mind is that same as in the previous part, we could overlap the accesses for the two vector loads, we can also do it here. So somehow, at some point, we will, in bank 0, at some point we will start with the second load, and we will, in order for the two vector loads to be complete, we will have to wait for bank -1 cycles more. Okay? So then we have the vector add, shift right, and vector store. This is same as before, 5 plus VLAN -1, 1 plus VLAN -1, and then we have the vector store, and for the vector store is going to be something similar to what we have here. So this is going to be 20, and then more accesses to bank 0, and finally bank -1 more cycles. Yes?
Sure. The hint would have been that the access latency to the memory is larger than the bank size for this exercise. So it can like fully pipeline memory because the access latency is larger than the amount of banks, also in the previous.
Mm-hmm. Yeah. But this doesn't change our timeline. It doesn't change the timeline. The only thing that changes is the fact that we are going to wait 4. So we are not issuing more requests. We will stop issuing requests, and then we will have to wait a few cycles until we get the first value from memory. But this doesn't really affect this timeline. Okay? Other questions? Okay, so yeah, so here it's how many of these 20 plus 20 plus 20 are we going to have? So this will be a function of the number of banks, because 16 is our vector length. We will have to repeat this 16, this 20, we will have to repeat it 16 divided by the number of banks. And this is for the first vector load. For the second vector load, we have the same, divided by the number of banks, plus this bank minus 1, plus 5, plus billion minus 1, plus 1, billion minus 1, plus, for the store, 20 times 16 divided by the number of banks, plus the number of banks minus 1. And this is equal to 170 cycles. And from here, we will get that the number of banks is equal to 8. Okay? Yes?
Could you not also from the text interpret that VR0 and VR1 are like consecutive, so you could say 20 times 32 over number of banks plus banks minus 1?
So I don't understand the question. Can you repeat?
In the text it says they are VR0 and VR1 are like consecutive.
Yes, they are consecutive.
So you could say that it's 20 times 32 over number of banks plus banks minus 1.
Is 20 times 32, yeah, I guess so. Okay?
Okay, that's
Any other questions? Okay. Thank you so much. What's the next one? Yes.
After this one, so okay. So after this one, we'll have a break as well. So this question is one of the questions that appeared in the final exam last year, which is about the Dram refresh. And for this question, actually, we are given multiple refresh policies, and based on these refresh policies, we are asked to solve the questions basically. So to do this, actually, we have a memory system where we have 8 banks, and each bank contains 32k rows. So let's just immediately calculate the total rows, which is total 18. So, and we also have a table where it shows like some certain rows, which shows the retention times of the certain rows given the temperature. So let's jump to the first question then. So we are given a refresh policy which is called the refresh policy A, and in that question we have a
refresh interval which refreshes all the rows in a DRAM, which covers the worst case retention time. What does it mean? So it means that given a temperature, it refreshes all the rows where according to a row where it has a lowest retention time. So according to this table, we will have our smallest retention time here, because it will always give us the smallest retention time unless the temperature is 0. So given that the A says that, let's assume that the refresh interval is 32 milliseconds. So what can be the maximum temperature so that the DRAM can operate reliably? So basically I will take this one and solve the T given the refresh interval, which is 32 milliseconds. So the T will be basically 96 Celsius degree, and so that the ReRAM can operate reliably given this refresh policy. So this was the first question. And it also asks what the command bus utilization is directly caused by DRAM refreshes. So command bus is defined as follows. So memory controller sends the refresh command, and the bus kept busy for certain time interval, which is 5 nanoseconds. So the command bus the utilization is basically what is the total time that the command bus is kept busy within a refresh time interval. So we can calculate it as follows. We know that all the rows will be refreshed, which is 2 to the 18, which will take 5 nanoseconds which will keep the bus busy 5 nanoseconds for each row. And for all of the rows, this will be the time that the command bus kept busy. And the refresh interval is 32 milliseconds. Okay, so this is basically the fraction of the command bus utilization, and this number will be, I believe, 0. Let me check. Yeah. So the percentage is basically this one. All right. So this was the first question, first policy, let's say. So for the second policy, it says that the memory controller refreshes the rows when it is needed. Basically, what does it mean? So given a temperature, if you need to refresh a row based on this table, the memory controller basically refreshes it. So we are given a temperature which is 64, and let's just directly calculate the retention time basically for this one, because the rest of them will be just the multiplication of the first row. So it will basically be 128 minus 64, and the retention time will be 64 milliseconds. So the question asks how many refreshes are performed by the memory controller during 1024 milliseconds period. So basically we need to find the number of refreshes for each of them. So let's find out. So the retention time for, let's make sure that this table is also visible. Anyway, so the retention time for the 2 to the 8 number of rows, here it comes from there, is 64 milliseconds, and then within that time period it will be that many times, right? So basically this will be the number of refreshes for that many rows. And for these rows, we will have that number of refreshes, because this is basically 2 times 64. And for this one, all other rows, we simply calculate it as total number of rows are 2 to the 18 minus 2 to the 16 plus 2, basically the number of rows that are visible here. So for that many rows, we will have that many refreshes, that number of refreshes, and for the last one, we will have that many refreshes. So if you basically sum these refreshes, you will get this number. So I won't do the math here, but this will be the result of this one. So this was the second policy. Let's jump to the third one. So basically, this is the same policy with the first one, where we take the worst case in the retention time, and then memory controller refreshes all the rows based on this retention time. And the retention time is actually given also here. So the memory controller will refresh all the rows for each 64 milliseconds. But there is also one more condition here. The memory controller will only refresh the row if it has not been accessed within that time interval. So if the row is accessed within 64 milliseconds, the memory controller will not refresh it. So basically, the first question asks this one: why is the case? Why can a memory controller should can behave like this? Do you have any guesses for this one? So why can it behave like this? Why can skip the row? Yeah.
Because the set is recharged on every access time.
Yeah. Was it the same for you? Yeah, that's basically the case. So when you access it, the cell will be recharged after it is sent to some amplifier. So yeah, this is the case. So let me formalize it. The charge of DRAM is restored basically when it is accessed. So this is the reason. So for the second one, we are given a program where the program actually accesses the rows with that fashion. Basically, for that many number of rows, it accesses each 1 milliseconds, and for that many number of rows, it accesses for each 60 milliseconds, and for the rest of them, it accesses for each 128 milliseconds. So, and the retention times are given for the rows that are being accessed in a given row. And the question asks here. Question asks what command pass utilization is directly caused by DRAM refreshes. So remember that the retention time was 64. So the refresh interval will also be 64 for all of the rows. But the program accesses these rows before refresh takes place in 64 milliseconds. So this means that number of rows will already be accessed. So we won't need them to be refreshed again, ever, because this guarantees that these rows will be accessed before a refresh takes place. So we basically say that for these there is no refresh takes place by memory controller, but for this one we can calculate it. So let's do it. So basically the number of rows left here is 2 to the 18 minus 2 to the 16 plus 2 to the 16. And this will be, I believe, 2 to the 17. Yes. So these are the number of rows that will be refreshed. And remember, the bus kept busy for 5 nanoseconds, so the utilization will be 2 to the 17 multiplied by 5 nanoseconds. So we need to divide it by we need to divide it by the refresh rate. But remember, the refresh rate will not be 64 anymore, because we will be refreshing those rows once for each once in each two refresh intervals. Okay, so the refresh interval will basically be 128, not 64. Okay, and this will result, I believe, like this. And this can be written as like this as well. Yeah. So the last question, the question for the last policy is a bit tricky. So we have a balloon filter for this policy, and the memory controller checks the balloon filter if the row is located. If the retention time of that row is basically defined by the first row. Okay, so if the balloon filter says yes, the memory controller basically refreshes such rows for each 64 milliseconds. If not, it will refresh it for each 128 milliseconds. So this is basically the policy of this memory controller. So if you remember, the balloon filter can't say no if the data is already there. Like if within the bit vector, within the balloon filter, if the data is already located, and if you ask for it, it can't say no. It will for sure say yes. There's a data there. But the other feature of the balloon filters is that it can say yes, even though the information is not there. So there is this false positive behavior of these balloon filters. So basically, what it means is that it can say yes. Like, for example, let's take a row which shouldn't be refreshed within 64 milliseconds. Let's say this should be refreshed in 128, and it says, like, is it located in the balloon filter? And if the balloon filter says yes, then this is false positive. Okay, this is basically what it is. So the question asks for the false positive rate. And we are given a temperature here. So as I said, it refreshes the rows that are located in the balloon filter for each 64 milliseconds and the others for 128 milliseconds. And it says that within that time interval, within 124 milliseconds, we have that many refreshes. So let's define P as the fraction of the rows that were a false hit in the balloon filter that should have been refreshed within 128 milliseconds. So this will be my fraction. Okay. So basically, let's write like this. So we have 2 to the 8 rows here, that should actually be refreshed within 64 milliseconds. Plus, we have 2 to the 18 minus 2 to the 8. This is the rest of the rows that should be actually refreshed within 128 milliseconds, and this is the fraction of the rows that were a false positive. Okay, so basically this is the number of rows refreshed in each, let's say, each 64 milliseconds, and this is our false rows. So, and how many times those are refreshed? So this is within that period. So this is basically number of refreshes for 64 milliseconds, let's say. Plus, we also have 2 to the 18 minus 2 to the 8 multiply minus 2 to the 18 minus 2 to the 8 multiply by I guess, yeah. So basically these are the rest of the rows that should be refreshed in 128 milliseconds minus that are actually refreshed here. Okay, and this is again the number of rows in 128 milliseconds. So if you sum this one, this number is actually given here. It's 2 million something. Okay, we already formalized it. So basically what you need to do is to find what P is. So if you do the math, the P will be this. Okay, this is the fraction of the rows that should have been refreshed within with the 128 refresh rate. So what is the number then? What is the number of the rows? It is okay, and this will give us. So these are the number of the rows that were false positive, that were hit by the balloon filter. And what are the total? And our fraction will be basically the total number of rows is this, and this is the false positive rate. And this is what the question asks for. Okay. Any questions? Okay, I guess not. So let's take a break, and after that we'll continue with the further questions.
Okay, so let's continue with the next question, which was in the midterm exam last year. So this was a bonus question. So it's about caching and processing in memory. So basically the question has two parts. In the first part, we assume a single core processor that has a cache. And then in the next part, we employ some processing in memory logic to offload this code here, and we analyze the performance in both cases. So the question starts with defining two integer arrays, A and B. A and B, they have starting addresses defined as this, and each element in those arrays is 4 bytes. And this is the code that is being executed. So in the first part, we have a single core processor. We have a, let me see. So initially, we don't have any caches in this part. We have 50 cycle fixed latency to the main memory. And here, what the question asks is basically what's the execution time of this code while we are ignoring the execution time of all non-memory instructions. So yeah, it is set here. Also assume that the execution time of non-memory access instructions is 0. Yeah, so basically what we need to do is we need to find out how many load and store operations in total are there in this code piece here, and then just multiply them with 50, which is the fixed main memory latency. So here when we look at the code, we have 2 load instructions and 1 store instructions. So we have a loop here, 2 loops actually, right? So the first label here is called the inner loop, and the second loop is called outer loop. So what happens here is, in the inner loop, we branch based on R4. R4 is incremented here, and then it's set to 0 here in the beginning of the outer loop, right? And then we branch when R4 is not equal to 2, meaning that we will repeat this inner loop for R4 0 and R4 1, right? And then we will increment R4 when it's 1, it will become 2, and then we won't take this branch anymore. So we iterate through this 2 times on each outer loop iteration. And similarly, the outer loop iterates 16 times in total, because we set it to 0 here in the beginning of the program, and then increment it by 1, and then branch 16 times. So this whole thing repeats 16 times. So inside the inner loop, we know that we have 2 load instructions. Those will repeat 2 times, because we iterate 2 times, and then we have +1 for the store instruction here, and then we repeat the entire thing 16 times. And the memory latency is 50 cycles. And this gives us the total execution time of this program here, which is 4,000 cycles. Yep. Okay, this is pretty simple, right? The first part. And yeah. Okay, so let's continue with the second part. So in the second part, we add a 128-byte private cache. So this was a single core processor, so it doesn't matter, but it's said to be private. So the cache block size is 8 bytes. So this means we can fit 2 elements into each cache block. The cache is direct mapped. That's important. Yeah, and on a cache hit, we can service a read and write operation in 5 cycles, as opposed to 50 cycles for main memory access when we get a cache miss. Okay, and the cache is initially empty. What will be the execution time of this program again? So here we need to inspect the code a little bit more to understand what is the access pattern to the elements of those arrays. So we know their addresses. From the addresses, we can find where they map to in the cache. So since this is a direct mapped cache and the size is 128 bytes, this means basically the the least significant 7 bits are used to find the set within the cache, right? And then if the lower 7 bits are the same, it doesn't matter what are the higher, the rest of the bits. If the lower bits are the same, this means that we'll have a cache conflict, right? Because we don't have multiple ways in the cache, it's direct mapped. So here we can see that the address of this, so this is a hexadecimal value. So here we have 3 zeros, which means 12 bits of zeros, right? So we have similar thing here for the B starting address. So this means the starting addresses of the 2 arrays conflict on this direct mapped cache. So if we access A0 and then B0, B0 will kick out A0 because they have conflict in the cache. So this is actually exactly what happens in this program when we look at it. So initially, the first load operation here will load A0, right? Because R5. So here, R5 is calculated by adding together R3 and R4, which are initially 0, right? So this will be A starting address plus 0. And then this will be R2 was the starting address of B. It will be B, and R4, we know R4 to be 0 from here. So this is basically the outer loop iterator. So I'll actually write it like this. So we first access A0, and then access B0. So since the cache is initially empty, we will have miss on A0, then we will have miss on B0. Okay. And then we know that this inner loop repeats 2 times. So we increment R4 here, and then start again with this. So this will load A1 this time, because R1 is 1, R3 is still 0. And the same for B. This will also load B1. So we do A0, B0, A1, B1 in this order. Okay, and for the store operation, this is R1 plus R3. R3 was the outer loop iterator. Yes, which is initially 0. So this will basically store register R7 to A0. So after completing those 4 accesses, we'll make another access to A0, which will be a miss again, because we touched B1 with this last access, which kicks out A1 and AB. So with each reference to A0, we bring both A0 and A1, because the cache block size is 8 bytes, but each element is 4 bytes, right? So we prefetch 8 bytes with each reference to the memory. Okay. Any questions so far? Okay, so I will continue with the access pattern here. So what happens with in the rest of the program is this R3 is incremented, which also increments the index of A, right? So in the next iteration, we will be accessing, so this R4 is reset to 0, right here in the beginning of the next outer loop iteration. But R3 is 1. We incremented it here, and it will stay incremented through the completion of this piece of code here. So in the next iteration, we'll load A1 first. And then for B, B is only B starting address plus A4, which is the inner loop iterator. So we'll do yes, we'll do B0 again. Okay, and in the next iteration, we increment A's index by 1, so we access A2, and then we access B1. Okay, so basically this continues like this, right? Yeah, we keep, in each iteration, we will keep referencing A by incrementing its like previous index values by 1, right? So in the next iteration, for example, we'll access A2, A3, and in the next one we'll access A3 and A4. But B always remains the same. Is it correct? So it's R4. We reset R4 here. Yep. It will always B0, B1. Let me check. Yeah. Okay, so only for the first few iterations, basically, until we get out of the scope of B0 and B1, we will get some conflicts in the cache, right? After that, A will start mapping to different sets in the direct map cache, so we won't have any other misses. Okay, so based on this access pattern, so I will write it here. So I think we understand what happens here now. So in the first iteration, let me write it like this. So in the first iteration, the access order is A0, then B0, and then A1, B1, and then we store to A0. In the next iteration, we increment the indices of A. So it's A1. We keep the B the same, A2, and B1, and A1. So this is what happens. In each iteration, we keep increasing the index of A, and we keep B's the same. A3, B1, and A2. Okay, so we see here that we have miss initially for this, A0. We have miss for B0. So we brought A0 and A1 to the cache, but B0 kicked them out. So we have miss here again. We have miss here again. And then we have miss here again. So in the first iteration, we have all misses. So since last here, in this iteration, we touched A0, it also brought A1 to the cache. So we get hit for this one. So I will use blue for hits. We get hit here. We get miss for B0 because we have conflict with A1. A2 maps to a different block, to different set in the cache. But this is a first time we touch A2, so we have miss here as well. And then B1, since we don't have conflict here with A2 and B0, B0 and B1 remains in the cache, so we get hit on this access. And then we get miss for A1 because A1 conflicts with B0 and B1. Okay. And then in the next iteration here, we already brought A2 to the cache, so this is hit. This is miss because it conflicts with A1 here. A3 is a hit. It came together with A2 when we referenced that, when we fetched that from the memory last time. We had B0 miss here, so we have B1 hit here, and then we have A2 hit here. So after analyzing this a little bit, it becomes obvious how this pattern would continue, but let's do one more iteration. I think after this iteration, it becomes obvious. So we do the same. We increment A indices, and we keep B's indices the same. This is A4, this is B1, and this is A3. Okay, so here we have completely independent sets being used in the cache for A and B. Right, so this A3 will be hit because we touched it here. B0 will be hit because it's still in the cache. A4 will be miss because this is the first time we access it. And B will be hit, and A3 will also be hit. So basically, this is hit. This is hit. So basically, after this point, we will have all hits for B's after the fourth iteration. And for A, we will only get demand misses, right? So for the first time when we bring corresponding cache block from A to the cache, we will get miss, otherwise we will get hits. And the pattern here repeats with basically only one hit after this point. Either only one miss here or all hits. So basically in the next iteration here in 5, when we do A4, B0, A5, B1, and A4, we see that this is a hit because we previously fetched this cache block. This is a hit, B still remains in the cache, and this is also a hit. But in the next iteration, when we try to access A6, we'll get a demand miss, right? So after this step, basically, we get the same pattern until we get to 16th iteration. Right, so we can easily calculate how many misses and how many hits we have based on this representation here. So it will be, so we can directly count the first 3 iterations. We have like 5 misses here, 3 plus 3 misses is 8, and then 1 more, we have 9 misses in total. Yeah, so we have 9 misses, plus how many hits in the first 3? It looks like 6, right? This one was a hit, yes, plus 6 hits. So this is for the first 3 iteration. For the remaining 13 iterations, we have, so the last one we'll finish with 1 miss, right? So let's consider the next 12 iterations first. And for the last one, we know that the pattern will be hit, hit, miss, hit, hit, right? So we'll end with this pattern. And the other 12 iterations will basically have this interleaving pattern here. So it will be, so we have 12 iterations in total. I will group them by 2. So it's 6 multiplied by 1 miss. So this is 1m plus 6 multiplied by 9 hits. Plus the last iteration was 4 hits and 1 miss. So if we add together those hits and misses, what we have in total, this is 54, 58, this is 64. I think it's 64 hits plus how many misses? 15, 16 misses. I think this is what we get, if I didn't do a mistake. I think it's correct though. Okay, and based on that we can calculate the execution time. So basically we multiply hits by 5 cycles and misses by 50 cycles. And if this is correct, then we should get 900 cycles. So let's do this multiplication. This is 320 plus 800. No, wait. And this will be 1,120, which doesn't match the solution here. Okay, so it seems like I did a mistake somewhere. Can somebody see where's the mistake? No? So I feel this pattern here is correct. So maybe we made a mistake while counting these hits and misses. So we have 5 axes in total. So one of them is a miss here. So it's 1 miss. So this will be 6 times in total, right? So here in between we have 12 iterations. And then 9 hits. And then 4 hits in the last iteration plus 1 miss. We have 6 hits here in this part, and then 9 misses.
I calculated the same answer as you did, but the answers in the midterm paper is wrong. 1,120 is the.
Okay, so I think it's possible that we made the same mistake. Did you solve it yourself previously?
In the midterm exam, I think you just omit the first 5 miss, so you didn't add 215 cycles in the very beginning. And the second iteration, you calculated to be 165, but it should be 160. So in the exam solution, there's a one place. The second iteration, you write 165 cycles, but it should be 160 cycles. It's two.
Okay, here you mean?
Yeah. So this
Right.
is one mistake.
Okay. Okay, then it seems like we have typos in the solution. Okay. Okay, if you have found the same solution independently, probably what we did here is correct then, I assume. Okay. Okay, was it clear what we did here? So I guess this question, solving this question correctly depends on like figuring out what this program here is doing and what is the access pattern. If you figure that out and if you don't make any mistakes while like calculating the stuff, I guess you can get to the correct answer. Okay, I will continue with the rest of the question. So in this part, we add a processing unit to the memory, which can access the memory with 10 cycle latency, right? But here we don't have any cache. So imagine that, so in this part, I think, don't do anything with the actual processor that we have defined in the previous two parts. So we only have some processing logic inside the memory, which can access the memory much faster, but it doesn't have any cache. And the access latency is 10 cycles here for both write and read operations. And the question is the same, how many cycles it takes to execute the same program using the memory processing units. And it doesn't have a cache. And similarly, non-memory access instructions are ignored. Okay, so basically, the solution of this part is simple as this A part, right? So again, we just need the total number of memory accesses, and then we will multiply it by 10 instead of by 60. So we already know that the total number of accesses is 5 multiplied by 16. So we just multiply this number by 10, and then 800 cycles should be the answer of this part. It's pretty simple, right? So yeah, the difference from this part is that we just changed the latency of the memory accesses, and the rest is the same basically. Okay, and we have the last part, the last two parts, which ask you to compare the processor with a cache to the in-memory processor without the cache. Yeah, and here the question is, so we see that in this part, that the in-memory processor was much faster than the cached version, right? So this was for the processor with a cache, it took that many cycles, and we reduced it to 800 cycles. So the question is, can we make the processor with cache better by increasing the capacity of the cache? And so basically, here in this question, you should just provide some reasoning why that could be the case or why that cannot be the case. Okay, and the answer here is no, because the conflicts we get are due to the fact that the cache is direct mapped, right? Just by increasing the capacity and keeping the structure as direct mapped won't help, because we will have the same cache conflicts in the beginning of the program that I showed previously. So we cannot avoid those conflicts.
I mean, could make it as large that bits count like 1 bit.
Sorry, can you say it again?
If you make it large enough that the bit where they differ. I mean, the error is like 1, 0, 0,
right.
8, 0, 0, and if it's large enough, then it could work out. but it's really large.
Okay, yeah, okay. That's correct, yes. Okay. Sure, yeah, okay. I think that might work. So basically, here you can, as long as you provide some reasoning here, I think both answers might be valid, right? So you can say, so the full answer would be basically, if you cannot increase your cache to something very big, no, it won't help, but if you can increase it beyond that point, such that those starting addresses map to different points in your direct mapped cache, then the answer will be yes, this may help. Okay, and the last part is kind of related to that. It asks you, what can you change in the cache design to kind of less expensively accelerate your program on the CPU. And here, instead of like making the cache like that big, much easier thing to do is probably most cost-effective thing to do is just to change the cache structure, right? So you can either increase the number of ways you have in your cache, right? So you can make it set associative or fully associative. And what else can you do? I mean, one option is to make it too large. Do you think there's another option? So I think in the answers we provided just the increasing the associativity of the cache. But do you think there might be something else to do? Can we, for example, increase the block size? Yes?
It's hashed address.
Hashed address. Okay, so instead of like using a direct map with a directly indexing based on the physical address, you're saying we can hash it and map it somewhere else.
No, just hash the address and use this to index into the cache.
Right. Okay. Yeah, that can potentially work. Okay, yeah, basically those two questions were kind of more open-ended, and it's possible to think of like multiple answers here. Okay, I think that was about this question. Do you have any other questions related to this? Okay, then we will continue with the next one.
Okay, so this next question deals with cache reverse engineering. And so we're given a problem here where we have to consider a processor that's using a 4-block cache that's using an LRU replacement policy. And so we're supposed to assume that starting with a completely empty cache, we have an application that accesses 3 different block addresses in a row. And here we're notating it by saying n plus 1, n plus 2, where the offset represents the starting address of consecutive cache blocks in memory, right? And so we issue this access pattern, where we issue n plus 2, and n plus 4, okay? And so we have these 3 accesses. So the first part of the question says that a malicious programmer realizes that she can reverse engineer the number of sets and ways in the cache by issuing 2 more accesses and observing only the cache hit rate across these 2 accesses, right? And so we assume that she can insert the malicious accesses only after the above 3 accesses, right? So we have n n plus 2, n plus 4, and then we have 2 more accesses that come after this. And so what we want to do is figure out which cache blocks we need to access in order to figure out what the cache, how the cache is structured, right? So okay, so this is sort of, you need to think about all the different cases here, right? So we're given that there's a 4-block cache, right? And so there's only a few ways you can actually organize a 4-block cache, right? So the first would be if it was completely direct mapped. So you have a cache that looks something like this, and we have 4 blocks. Another option is if we have if it's two-way associative, and then the third option is if it's completely fully associative, right? And so those are our only 3 potential cache configurations that we could have. And so now we want to figure out what 2 additional accesses we can do in order to figure out which one of these is the actual cache that's being used here. So here we have to start doing a bit of cache simulation. So I'm going to move to a separate sheet so we have a little more room. So for each of these 3 options, we can simulate what's already happened for this cache, right? So if we consider the first cache organization, we issue these 3 accesses, n plus 2, and n plus 4, then we can figure out where they go. So let's say n goes to this first block here. Then n plus 2 would map to down here. And so I'm just going to say n sub 2 for n plus 2, right? Just to save some ink. And then we issue an access to n plus 4. And so n plus 4 actually comes back over here and conflicts with n. And given that we only have one way, this one simply gets replaced by n plus 4. Okay? And so that's our state of the cache after these 3 accesses. So for the second cache configuration, we can do the same thing, and we figure out what's going on. So here we issue an access to n, and then n plus 1. n plus 2 goes back here, so n plus 2 is over here. And n plus 4 actually maps to the same set as well. So here we have to deal with our replacement policy, right? And so the least recently used in this case is actually the n. So we kick out the n, and now n plus 4 sits here. And with the third cache organization, if it's fully associative, all 3 just end up in different ways here. So we have n, n plus 2, and then n plus 4, right? Okay, so this is our state of the cache after these 3 application accesses. So we want to figure out what 2 more accesses we want to do in order to differentiate these 3 cases, right? And so there's a couple of ways you can avoid doing some excess work here. I'm going to go through and show all the different possibilities just to demonstrate what this looks like. But so first so one assumption we can make here is that. So okay, sorry, it's not an assumption, but what you can observe is that if we access anything else other than n plus 2, and n plus 4, they're guaranteed to be misses, right? So let's say we access n plus 1. In any of these cases, that doesn't exist already, and so it'll just be a demand miss. And so what will happen is we'll just end up missing with all 3 configurations, and there's no way we can differentiate them. So it's actually uninteresting to consider those cases. So we can just consider the next 2 accesses being one of these 3 ones that we've already done. All right, so let's start with the first cache configuration. So first we can access n, n plus 2, or n plus 4, right? And the second access can also be those 3, so we're just going to consider all the cases here, n, n plus 2, and then n plus 4. And we can build a table of what the hit and miss ratios look like, because that's what we're concerned with, right? We just want to look at the hit ratio over these next 2 accesses and decide what's going on. So here, let's start with the first access, right? So let's say this is the first access. So if we issue an access to n, we see here that it will miss, right? So we'll get a miss. In all 3 of these, the first access will be a miss. The second access in each of these cases will be a little different, because if we go and do this, then the cache will now, n will come, it'll replace n4, so our cache state will look like n and then n2, right? So now we can go through these 3 options. So the second access, if we issue n again, it will be a hit. If we issue an access to n2, it'll be a hit. But if we issue n4, it'll be a miss, because it will come here and replace this n, right? So we can just repeat for the other columns here. So if we issue n2 as our first access, that'll be a hit. So in all 3 cases, the first access is a hit, and the cache state will be unchanged, right? So then for the second access, if we issue an access to n, then it'll come and replace n4, and so that'll be a miss. n2 is already there, so it'll be a hit. n4 is already there, so it'll be a hit. And this third column, n4 is already there, so first it's a hit. And the second column actually looks exactly the same, because we're starting with the same cache state, right? So it'll be a miss here, a hit here, and a hit here. Okay? So this is what these two axes could look like no matter what you do. And if you had any other axis here other than n, n2, and n4, it would just be a miss, right? Okay, so we can do the same exact thing for this second cache configuration. So if we do n, n2, n4, and build our table again, n, n2, n4. Okay, so if we issue an access to n first, it is not already in the cache, and so it'll be a miss in all three cases, right? And so in this situation, the cache, so n will come and it will replace the LRU position, right? So here in our original access pattern, we issued n, n plus 2, and n plus 4, which makes n2 the least recently used one. So n will come and replace that. So our cache configuration will look like n4 and n after this first access to n. So the second access then, n will be a hit because it's in the cache, n2 will be a miss, and n4 will be a hit, okay? And so if we do n2 first, then that'll be a hit in all these cases. And this cache configuration after this will look exactly like this. However, n2 will now be the most recently used, and n4 will be the least recently used, right? So if our final access goes to n is not in the cache, so it will miss. n2 will be in the cache, so it'll be a hit, and n4 will be in the cache, so it will also hit. Right? And so we can similarly say that this pattern will look pretty much the same because n4 starts out there, and n2 is already there, so this will again be a miss, hit, and a hit. And for the third cache configuration, it's actually much easier because all three of these are already in the cache. So no matter which configuration we do, it'll be a hit and a hit, right? Because no matter which ones you access, they're already there. Okay, so based on this particular, all these different possibilities, we can find one access pattern that will let us differentiate these three cases, right? And so it turns out there's actually two different configurations that allow this. So if we look at this column, n first and then n2 second, here we have a miss and a hit. Here we have two misses, and here we have two hits, right? So if the next two accesses were n and then n plus 2, then we could differentiate these three cases and figure out exactly what happened. So one particular solution is n and then n plus 2. But it turns out there's actually a second solution as well, and that's the case that's right underneath. Because here we have miss-miss, here we have miss-hit, and here we have hit-hit. And so that solution also works. And so there's two solutions to this particular problem. So this will be if the first axis is n and the second axis is n4, right? And so in either of these three cases, we have different hit rates, right? So here only one of them hits, here none of them hit, and here both hit, right? Okay, so over here in our actual problem, we can just pick one of these solutions, right? So I'm not going to write it again, but it's essentially these two right here. So the second part, are there any questions about going through that? Okay, so the second part asks you to actually implement this a little bit. And so how many L1 sets and ways would there actually be if the cache hit rate were all of these different possibilities? So we've already done all the legwork for this. And so depending on which solution you pick here for the first part, you would simply fill in this table as appropriate, right? So I'm going to give the example of filling in, let's say, this first access pattern. So if we're going to issue an access first to n and then to n2, we're dealing with this particular situation. And so if the L1 cache hit rate we observe to be 100%, that means we're in the third configuration, right? So in this configuration, we have one set and we have 4 ways. If we observe a 50% hit rate, that means one access hit and the other one missed. So it had to be this configuration. And so here we have 4 sets, but just one way. And then the last one where we miss in both has to have 2 sets and 2 ways. Okay, so that's pretty straightforward. So the third part of this question asks us, what should the 2 next accesses be if the replacement policy had been most recently used instead of LRU? Okay, so we're essentially doing the same thing we did for the first part, except we're changing the replacement policy. And so this is actually quite a bit easier than it might seem. We don't have to repeat this whole thing again. Because if you notice, in this first cache configuration, the replacement policy doesn't even come into play because there's only one way. And so this table looks exactly like it did here. For the second configuration, the replacement policy is actually important because it'll determine which line we kick out. And so we'll have to repeat this analysis. But for the third cache configuration also, the replacement policy doesn't come into play at all. And so what we're going to do here is we're going to redo the simulation, assuming a most recently used policy for configuration number 2. So I'm going to draw this table again. Okay, so for this configuration now, we're going to, the starting state of the cache will look like this, except this time, the most recently used will be N4. Right? So when we begin doing this, if we access N, then we're going to kick out the most recently used. And so it's going to replace that, and we're going to end up with a cache state that looks like N and then N2, right? And so this will be a miss because this doesn't already exist in the cache. But this new configuration will change how our second access looks. So the second access here, if we issue N, it will be a hit. If we issue N2, it'll be a hit. And if we issue N4, then it'll be a miss, right? So these two have essentially swapped places. With the N2 access, we'll see that in all of these cases, N2 isn't there. And sorry. Yeah, so we're starting with this initial state of the cache, sorry. So yes, in this case, N2 is there, and so the first access will be a hit in all 3 cases. And the second access will essentially look just like it did for this case, right? So if we issue N, it's going to miss. If we issue N2, it's going to hit. And if we issue N4, it's going to hit. And N4 is essentially the same thing because it's already there. And so it's going to be a hit in the first access. And in the second access, N is going to be a miss, and these two will be hits, right? So this is the only new piece of information we have for this part of the problem. And so now if we look at all these different configurations, we can try and figure out which access pattern will allow us to differentiate these 3 cases. And it turns out there isn't one, right? So in none of these access patterns do you get different hit rates for all 3 caches. And yeah, so essentially our answer to this part is that there is none, right? So there's no solution. And there's no way to do this with an MRU cache. Okay, any questions about that? Okay, so then we move to the second part of the problem, which is called exploitation. So if we assume that we have the original cache design, which uses an LRU replacement policy and uses this configuration, 1 set and 4 away. So essentially we have this giant fully associative cache. We decide that, so the malicious programmer decides to disrupt an application, blah, 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 by using a carefully designed concurrently running process, right, to interfere with the banking application that's running. We want to induce slowdown. So we are given this particular access pattern, right? So the unmodified application issues this pattern where, again, these numbers represent cache block offsets, right? So x representing n plus x. So this is essentially n0, this is n6 in the notation I was using before. So the first part asks us, what is the unmodified application's cache hit rate? So this is a straightforward simulation. So we essentially simulate this access pattern going through our cache. And so I'll go ahead and demonstrate how you might do that. So we have our access pattern here. And so we start with an empty cache, right, as the problem specifies. So okay, actually I'm going to use a new sheet so it's clear. Okay, so we have this access pattern. And yeah, so I'm going to draw out an empty cache here that we can start working with. Okay, so the first access goes to address 0, and so this is just going to be a demand miss, and so we're going to allocate that here, right? And then so 6 is also going to be a miss because it doesn't exist. 1 doesn't exist. 7 doesn't exist. Okay, so now we get to 6, and so 6 exists in the cache, so it's going to be a hit, right? 1 also exists in the cache, so it's going to be a hit. 4 does not. So 4 is going to be a miss. But now we have to figure out where to allocate it. And so since we're using a LRU replacement policy, we just figure out what's the least recently used here, right? So we have 0, 6, 1, 7 in the cache. And so 1, 6, 7. And so 0 is actually the least recently used. So we replace 0 with 4. And then we keep going. So next access is to 0, which we've just kicked out. So it's also a miss. And so we do the same thing. Now we have 4, 6, 1, 7 in the cache. And so 4, 6, 1. So 7 is the least recently used. So we kick out 7 and replace it with 0, right? So now we access 5. Again, it's a miss. So we determine out of 4, 6, 1, and 0, what's the least recently used, and so that's 6. So we replace 6 with 5. Next access goes to 0, which is a hit. 7 is no longer in the cache, so that's a miss. And so out of 4, 5, 1, and 0, we have 5, 0, 4. So 1 is the least recently used. And to replace that with 7, then we have 4, which is a hit, 2, which is a miss. And so out of 4, 5, 7, and 0, 4, 0, 7. So 5 is the LRU. So we replace that with 2. Then we have 7, which is a hit, 2, which is a hit, and 4, which is a hit. Okay, so now we figure out, just to calculate what the hit rate is, it's just however many hits we had. So we have 1, 2, 3, 4, 5, 6, 7 out of 16 total accesses. Right? So the answer here is just simply 7 out of 16. Okay, so it's just straightforward cache simulation. Okay, so the second part of the problem says that assume that the malicious programmer knows the access pattern, which is given here, and using this information, she's able to inject a single extra cache access in between each of the banking application's accesses. Right, so this is the same as saying that she can interleave a malicious access pattern with the normal execution, with the normal application's access pattern. And so now we want to figure out what is the minimum possible cache hit rate, not counting the extra malicious accesses, that the malicious programmer can induce for this banking application. And so this could be kind of complicated if you try and approach this by figuring out what all possibilities are between here, right? But if you observe that when we have this application access pattern, and given this fully associative cache, the way to force something to not hit is to ensure that at least 4 different accesses have occurred in between, right? So if we have something living in this cache, if we issue 4 accesses to something else, then we'll have fully evicted this cache. And then when the access to that first cache line comes again, it'll be a miss, right? So what we want is that we want an access to 4 different cache blocks in between 2 accesses to the same one. So if we go look at this initial access pattern, right, we want to see where are cases in which we actually can't do this, given that we can insert 1 extra access in between all of these. So let's start at the beginning, right? So with 0, the next access to 0 is quite far away, right? So excuse me, there's no way that 0 will hit with a malicious access pattern in between. So at 6, we have 1 and 7 in between. And so if we can insert extra accesses here, that's a total of 5 potentially unique accesses in between, right? So we're okay here. There's no way this will hit. So we can ensure that the next access to 6 will be a miss. And so we keep doing this down the line, right? 1, the next access to 1 has another 5 potential accesses in between. And so we're good there. Between 7 and the next access 7, that's quite far away, so we're good. The next access to 6 here doesn't happen. The next access to 1 is it also doesn't happen. 4, same case. Between these two 4s, we have many accesses. So the first interesting case is with 0. So the next access to 0 occurs here, right? And so no matter what accesses we issue in between these two, we can't guarantee that this next 0 will miss, right? Because the 0 will be in the cache. We'll issue 3 random accesses, which will fill up these slots, potentially evicting whatever was there before. And the next access to 0 will hit no matter what we do. And so this is the first case in which we can't prevent anything. And so this 0 is guaranteed to hit, essentially. And so we continue. We have a 5, nothing to worry about. The 0, the 7. Between the 7 and that 7, there's enough space. 4, it's fine. Here's another case. We have 2, an access and 2. And so this 2 is guaranteed to hit no matter what we can do. And that's the last case, right? So if we issue the worst case possible access pattern we can do here, we'll still have 2 hits in the original banking application, right? And there's nothing we can do about that. So the minimum cache hit rate that we can induce is a 2 out of 16. Okay, are there any questions about that? Okay, that's the last part of this question. So, all right, next one then. I think this isn't even on.
I'm not sure if it's working. But
yeah.
Right, so for this question about emerging memory technologies, it's a bit straightforward and easy question. So you have a computer scientist at ETH developed a new memory technology. They call it Eth Ram, which is non-volatile, and the access latency of this RAM is close to that of DRAM, while to provide higher density compared to the latest DRAM technologies. So this RAM has shortcoming, which is limited endurance. So, which means the memory stops functioning after some series of write requests to that memory. And basically, it's 10 to the power 6 write request, then the cell will wear out, which means the RAM will be useless in this case. So we have a student, female student, and build a computer system using 1 gigabyte of this RAM, and this is very important basically. So she exploits a perfect weir leveling mechanism, which means there is a perfect distributor that distributes those write requests to all cells. So you have fair write requests among or all over the RAM. So this student now worried about the lifetime of the computer system she built, and she execute a test program. She want to know basically after how long the RAM will be useless. And she figured out that after a year, exactly a year, this Eth RAM will be useless. So you have the following assumptions. So the processor is in order and there is no memory level parallelism, which means that you have all those write requests serially sent from the processor to the RAM. And you cannot write more than one row per time. So everything in serial fashion. And it takes 5 nanoseconds to send a memory request from the processor to the controller, and then from the controller to the RAM, it took 28 nanoseconds. So basically this RAM is word addressable, thus each write request write 4 bytes for each write request. So basically you could assume that this is the RAM and you have rows. The size of this RAM is 1 gigabyte, and you need to know basically how many rows you have there. And yeah, sorry, the question is ask you to find the write latency of that RAM. So you already know that this RAM will be wear out after 1 year, and you have all the latency requests from the processor to the controller, from the controller to the RAM, and you need to figure out basically the write latency. So how many rows we have in this RAM? If you know that the one row is 4 bytes, then obviously 1 gigabyte over 4 bytes, you will get how many rows there. And each row has many cells, and each cell will wear out after 10 to the power 6 write access to that cell. So basically the time to wear out the entire RAM is equivalent to how many rows and how many times you are able to access that row at most, plus the delay to send the write request to the RAM and the write latency. So basically, this is equivalent to 2 to the power 30. You divide over 2 to the power 2 to know how many rows, and each row you could access it at most by 10 to the power 6, and then multiply by the total time needs to access that RAM and write some data, which is basically 5 plus 28 plus the write latency. So let's call it write, for example. And this is equivalent to 1 year. So now you need to make sure that all the units are consistent in this function. So here you have byte, byte, And here you have nanosecond, nanosecond, so this should be nanosecond, as well as the 1 year you need to convert it to nanosecond. So then you'll have your function, which is 365 multiplied by 24 hours per day, and then convert it into seconds, multiplied by 10 to the power 9. Okay. So basically you could divide this over, so we have 28, so you could divide over 2 to the power 28 multiplied by 10 to the power 6. This will give you 5 plus 28 plus the t right. So this is 32, 33. So you could move it to the other side, and then you will get the write latency, which is equivalent to 84.5 nanosecond. So this question is straightforward, easy to solve, I guess. So do you have any questions? All right, cool. So let's proceed to the second part of this question. So now you need to follow the exact same procedures, but you need to change a bit in the design to improve the lifetime of this DRAM, or sorry, the ETH RAM. So basically they assume that the previous design has 2 bits in each cell, and now they will reduce it to 1 bit. And this affects the lifetime of each cell, and they improve it by 10x. However, this as well decreased the write latency by 70%. So now you need to calculate the same steps to get the new lifetime of this ETH RAM. So let's start from the 10x. So basically, in the first part, the cell was will wear out after 10 to the power 6. So now 10x higher. So basically, it will be 10 to the power 7, right? So 10 multiplied by 10 to the power 6. And the write latency decreases by 70%. So the write latency in the first part, we calculated as 84.5. And now we need to have 30% of that time delay for the new ETH RAM. So the new TW2, let's call it, it's 30% of the 84.5. So now you have everything ready, except one thing. We reduced the number of bits to be stored in each cell from 2 to 1. This directly affects the storage or the capacity of this ETH RAM from 1 gigabyte into half, right? Because we reduce the number of bits stored there to half. So this gives us, so now we want to calculate the total time to wear out. So we have 2 to the power 30 minus 1, right? Because we reduced the size to half. And now we have how many rows there? So each row can afford 4 bytes, same thing, 2 to the power 2. Now multiplied by the new lifetime for each cell, which is 2 to the power 7, multiplied by the total time needs to send the request to the controller, from the controller to the RAM, and then the write latency. So however we change the write latency, we improve it by 70%, and we have the new one calculated as 25.35. So we have the same time needed to send the request to the controller and back to the RAM, which is 5 plus 28. Sorry, this is plus. So this will give you directly the answer, which will be 2.5, almost 2.5 years. Any question for that? yeah, just straightforward, right? All right, thank you.
Okay, so we have 2 questions left, but just 10 minutes. So I will just ask you to look at the solutions of this question. This is from last year's final exam. This was the last question that we were going to solve today, but I think we won't have time for this. So I encourage you to look at the all other questions in midterms and exams as well. Just to remind it, here this is the course wiki, right? And in the exams, you see all these solutions and questions. So let's start with the question, the first question that I'm gonna solve. So this is branch prediction question, right? And we have an in-order pipeline with 12 stages, and it's a single cycle, blah, 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 okay. And we have a program with 1,000 dynamic instructions, and it takes 20 to 11 cycles here, and 200 of those instructions are conditional branches, right? So, okay, here the thing we don't know is how much time do we spend to understand the results of the branch? And the question is asking for that. Branch instructions are resolved when? Okay, so what do we have here? So since we have a pipeline, first we need to fill this pipeline, right? So we spent 12 cycles for this. And when we spent 12 cycles, we are already get rid of the first instruction, right? So it's already committed. So after 12 cycles, we have 1,000 plus minus 1, 1,000 minus 1 other dynamic instructions. So we can safely assume that these all are gonna take just 1 cycle, since this is almost ideal system. But only thing we have is, other than these is we have 200 conditional branches, and they lead to stalls for X cycles, right? And when you sum all these up, question tells us that it takes this many cycles to finish this program. So when you do the math, actually X becomes 6 here. It's not very hard to do that, so you can just look at it. Okay. So the second part of the question is more interesting. So to save time, I just wrote some things, but let me explain the question first to you. So we work on the same design, but we have a mysterious branch predictor here, right? And this mysterious branch predictor sometimes predicts wrong, sometimes predicts right, and then it saves us some cycles. And we have this following program. Don't miss this program with this 1,000 dynamic instructions. This is a separate program here, and it takes 115 cycles, right? So what I do usually whenever I see a code is, I draw something like this here. So this tells me what this code is doing. So it's better to understand what the code is doing here. So we have 2 loops here, and we can start with the loop 2, for example. So it looks at the value of R2, and it increases the value of R2, and there's an unconditional branch back to the beginning of loop 2 here, right? Okay, so this part can be drawn like this here, right? Okay, so whenever this loop is completed, it jumps back to loop 1, right? And then in loop 1, we look at the value of R1, which is controlled here, and then this also iterates. So the important thing is how many times do we iterate over these loops. So the first one is iterating 3 times, right? R2 goes from 0, 1, 2, iterates, and then when it reaches to 3, it goes out of the loop. And then for the first one, it iterates for 5 times, and the 6th time, it goes out of the loop. Okay, so let's look at the questions. So when we look at the questions here, we see, okay, actually, yeah, you need to look at here first. So we have this mysterious branch predictor, and we need to understand what kind of branch predictor this is, right? We are doing some reverse engineering here. So, and the questions are like, can this be a static branch predictor, or can be a last time branch predictor, or backward taken, forward not taken, or 2-bit counter based. So we are going to look at all these options after we understand how these branches work here. So the thing is, okay, I'll come to green calculation later. So here I just draw, can you see this? The paper is closing, okay. Okay, we don't see the code. Yeah, here we see everything. Okay. So when we first see the first branch, it's not taken, right? Then we get into the loop because R1 was 0, and if it's 5, no. Then we get into the loop. So it's not taken. So branch 1 is this one, and branch 2 is this one. And then we go to the branch 2, and then we iterate 3 times here, right? For the first iteration, R2 is 0, then 1, then 2, then 3. And when it's 3, then we take this branch and jump back to the beginning. So this is the pattern we see in this program, right? And then we iterate over with this pattern for 5 times. And then at the end, we take the first branch and go out of the loop. So this is how it works. Okay, so to decide which kind of branch predictor are we dealing with here, we need to understand the execution time of this as well. So let's look at the calculation here. So in the inner loop here, we have 3 instructions, right? And this iterates 3 times. So 3 times 3 plus 1 is at the end of last iteration, it goes back to branch equal, and then it executes it as well, and then jumps back, right? So it's like 3 times 3 plus 1 instructions are executed in this loop. And then it goes back to here in the loop 1. So in the loop 1, how many instructions do we execute? So this is 10 instructions in total, right? The loop 2, this part. This part is 10 instructions. And then we are looking at this part as whole. So here I have 3 instructions, and then this 10 instruction section. Okay, then we have 13 instructions here, and it iterates 5 times, right? And then there's also another plus 1 here for the last execution of this last branch when it gets out. Okay, so when we calculate this, we see that we have 66 instructions in this loop 1, including loop 2 as well, right? Okay, so as it's the same design, we still have a pipeline with 12 stages. And to fill this pipeline, we spent 12 stages in the beginning of the loop for this particular instruction. Okay? And then at the end, we have another instruction here, and it just costs for one cycle. So when we sum them up, 12, 66, and 1, we have 79 cycles, right? If we have a perfect predictor, if we don't have any stalls because of the branch, then it should take 79 cycles. Okay, so but each misprediction costs us 6 cycles of bubble. So we calculated it here, right? Oh, by the way, I forgot to mention that the question here is asking when the branch instructions are resolved. So since I have 6 cycles of bubble here, the answer is at the end of 7th cycle. Okay, just to note it. From the A, we have this 6 number, and the calculation is easy. So this is the perfect condition, and then we have 6 cycles for n mispredictions. And then when we sum them up and calculate, we see that we need to have 6 mispredictions. So in whichever configuration of branch predictor, I see 6 mispredictions. I can say that it's the one that we are using here. Okay, let's look at them one by one quickly. Do we have time, by the way? Oh, we don't have time. Okay, what should I do? Summarize? Okay. So here we have a lot of not takens, right? And we have 6 of the takens. So if I predict not taken for aesthetically, always not taken predict, then I miss only 6 of these, right? So it matches with this number. So it's one of the options that we see here. Static branch predictor, always not taken. For last time branch predictor, whenever you switch between not taken and taken, then it costs you a miss, right? So here, when we look at the switch, here you see it at 6 takens, we have actually 10 or 11 switches here. So it's not going to be the case. Backward taken, forward not taken means that if the branch is going backwards, then it's going to be taken. But statically predicted taken doesn't look like a wise decision here. We have a lot of not takens, so it's not going to be the thing. And if you look at the 2-bit counter-based prediction, in which you have these states, strongly not taken, weakly taken, strongly taken, you can see that you need to mostly predict not taken, right? And if you just try this with these configurations, you will see that strongly not taken and weakly not taken fits to our case for both local and global cases. So you can, I guess, cover the material about what are these, and I think I'm gonna finish here because we ran out of time. I think that's all. Yeah, solve the questions and good luck with the exam. Thank you.